feedback forms, I hope. If any of you don't have feedback form, I will get it for you at time 11 o'clock, 10:30. Please return the feedback form by this afternoon at tea time when the office staff will come here downstairs at the tea place where we had tea yesterday. At that time, you can also collect your TA, and you will also be given some participation certificate. Today's speakers, we begin with Sunder, and after Sunder, Vijay Kudiyalam will give a lecture on algebra, and then the afternoon, Vishwanath and Anirban Mukhopadhyay.
Okay, so so this is what I want to talk about today. So so let me begin by asking you a question. This obviously stems from this word, exponent. Can you tell me what the word exponent means? What do you use exponent for in mathematics? Huh? Power. So in this, what is the exponent? In what I've written here, this is the exponent, right? So it really comes from, there is a function that comes from our trying to understand things like we add 2 to the 4, then we know that 4 is the exponent in this thing. Okay, so we all know what 2 to the 4 means. So what does 2 to the half mean? That requires little more effort. Right. What does the number 2 power square root of 2 mean? That requires considerable more effort and ingenuity to give good sense to this word. Okay, so I want to describe, start talking. Okay, let's look at powers, which we first do in school and college. So you want to define a power n. So first, for n, a natural number, then we all know what this means. We know that we just means multiplying a by itself so many times. And it's there we know that it satisfies this rule, a power m into a power n equals a power m plus n. So we take this as the guiding rule, that whatever this function, we want to talk about a power x, whatever that function as a function of x, we would like that to satisfy this simple natural property that holds for when x is a natural number. So the first stage, what you observe is that if you want to define it for n in non-negative integers, then you must define a power 0. And this is our key, this is our guide to how you must define it. So it is clear that a power 0 should be defined as 1, right? So no matter what a is, this is what you have to define it as. Okay. So persisting with this analogy, you want to define this for all integers. So if n is negative, then you will want to define this as 1 by n, a power n. So that this equation continues to hold. And then we see that yes, indeed this equation holds. We have successfully defined a power x for all integers x now, not just for positive numbers, not just for positive integers. Okay. So the next stage is to go beyond integers. So like in arithmetic, you start with positive numbers, then 0, then integers, and then you start getting more ambitious. You introduce multiplication, and then you want to be able to talk about fractions. That is the next stage of development, right? So we want to go to fractions. So for that, the thing we note is that analogous to this, we have the multiplicative version of this is that a power m, the whole power n, is, we all know this standard rule, a power m times n. So this is how it is defined for, and this rule is satisfied when m and n are natural numbers. And so we would naturally like this to hold in general, right? Okay, but now you have to be a little careful. How does one define a power no, so whatever, see you would like to define, you would like to define a power 1 by n. So what would you want to define it as? That means you'd want this to be a solution of y power n equal to a, right? This is how you want to define it. Already you run into one stumbling block. What do I do, for example, for minus 1 power half? You want the solution of y squared equal to minus 1. And that you don't know of these such animals, at least in school before somebody teaches you these artificial, imaginary quantities. And so to define, see, for example, you would, if you wanted to apply this for negative numbers, you would expect minus 1 squared, which is a perfectly good number. You can make sense of minus 1 squared. But then you would expect this to be equal to minus 1, right? Which you know is not true. This is just 1, it is 1 squared. So, and it is true with a pinch of salt if you allow a negative square root and so on. So we haven't made, so we want to say the solution, or the positive solution. So by nth root, that's what you mean usually, right? And so you do this provided a is positive. If a is positive, then you can do this. Why is that? Because if you look at the function y power n, I still have a little problem with that. So, okay. So we only want to try defining it for positive numbers. We want to define powers only for, we want to define rational powers and so on only for negative, positive numbers. That is the problem with minus 1 times this, that we should steer clear of there for a moment. Okay, so we'll come to this. So we want to systematically define x power r, where r is a rational number. First, I called it a before, I'll call the variable x now. So how would one define this thing? Well, r is a rational number means you can write r as some m by n. Right? So for positive x, we define this as positive solution, the positive solution y of what? We want y power n to be x power m. Right? So x power m we know how to define, and we want to take the positive. So how do you know that we can do this? Because if you look at the function y going to y power n, yeah. Now this, when y is 0, it is 1. And as y goes to infinity, then you know that this goes to infinity. So if you draw the graph of this function, you know that it's going to be something like this. Something which blows up to infinity. Huh? Oh, sorry, y power, sorry. It looks something like this. Yeah, I was looking at putting 0 in the wrong place. Okay. So we're not going to look like this. So at 0 it is 0, and at plus infinity it goes up plus infinity. So if you take any finite number, then by the intermediate value theorem, you know that because this function is continuous, this will cross any horizontal line that you would want to impose, and so there will be a unique solution for this. And so that unique positive solution is what you call x power m by n. Okay, so now you define x power r for all rationals. And it is clear that various things hold, that x power r is increasing in r. As a function of r, it is increasing. If you take larger r, you will have a larger power. And you define this function, which is a positive increasing function. For all rational numbers, you have defined the function. Now, how would I define x power square root 2? You would expect this to, I want to define x power t for any t. See, this satisfies, still it satisfies the good properties, x power r plus s is x power r into x power s, and x power r power s is x power r s, provided you stay inside rationals. Now if you want to go outside rationals, you would still like this to hold. So you want to define x power, for example, I want to define 2 power square root 2. You can do it any way you want. You can take square root 2 and you know that, for example, it has a decimal expansion. It is a non-terminating, non-recurring infinite decimal expansion because it is irrational. Okay. Then what you can do is you can write this as limit of some Tn, where Tn is the nth truncation of this expansion. Right? So Tn increases to square root 2. So Tn are rationals, and they increase to square root 2. So you'll know that 2 power Tn is going to be an increasing function. Right? And further, in fact, if you take for all r in Q, you take r bigger than square root 2, then you can see that 2 power Tn is going to be less than or equal to 2 power r. So what you see that 2 power Tn is an increasing sequence. They are all bounded by 2 power r for any r bigger than square root 2. So what do you think 2 power square root 2 should be defined as? There is only one natural way. You expect 2 power t to be a nice function of t. You want the function of t to satisfy these rules in t, and you want this to be continuous. But then what can 2 power square root 2 possibly be? It has no choice. It must be defined as the supremum of all 2 power r, where r is the rational less than square root 2. So now you have succeeded in defining powers, even irrational powers of arbitrary numbers. Okay. And what you must okay, then in fact one going to show that if you look at t going to a power t, if a is positive, is a function which satisfies all those good properties that we wrote down. A power t is increasing in t, and all the rules of exponents, that a power t times a power s will be t plus s, and then a power t whole power s will be a power ts, and so on, and usual rules. In fact, with a little bit of work, one can even show that this function is continuous in t. Right? I would urge you to sit down and try and prove why this is true. Why this animal that you have defined is in fact continuous function of its argument. In fact, let me show you that in fact it is even more than continuous, it is differentiable in t. Why is it differentiable in t? Let us look at, I want to say this is differentiable at t, so I should look at a power t plus h minus a power t divided by h, limit as t goes to 0. I will show that that limit exists. Then it will show that this function is differentiable at the variable t. So let me take t naught so that you know that t naught is temporarily fixed. Okay. So, but this you observe, because of the law of exponents, you can take out an a power t naught from both terms. The t naught doesn't play a role in this thing at all. This is just a power t naught into limit as h goes to 0, a power h minus 1 by h. So it is the differentiability is really only equivalent to proving that this limit exists. Okay. Okay. And in fact, that this limit exists for any one a is the same requirement. Then it will hold for every a. Because if you take any other b, if you know that there is a continuous function, increasing function in h, when h goes to minus infinity, it will go to 0. And as h goes to plus infinity, it will go to infinity. So in between, it will cross every level. So this a power h going to a power h will map the positive real, will map the real line onto the positive line. Clear what I'm saying is that as h ranges over the real line, or t is the real line, you go to a power t in the positive line. Then this function is continuous, and it is onto by intermediate value theorem again. So any b can be written as any a power h. So it follows that if this limit exists for one a, that means that this function a power t is differentiable at t equals 0, and hence by this calculation it is differentiable at all t0. In particular, it will be differentiable at that t0 for which a power t0 is b. And then it will follow that this limit b power h minus 1 by h will also exist. So I'm saying, so this is a universal phenomenon, and in fact the existence of this limit is independent of the parameter a that you choose. In fact, what one is saying is there is one special number. There exists one special real number e such that limit as h goes to 0 e to the h minus 1 by h equal to 1. Right? There is a unique real number of this property. So this pins down that number absolutely unique. There is a God-given number with all these wonderful magical properties, and what you're saying is that any number b can be written as e power t for some b. T, there will be a function of b. For every t positive, for every b positive, you can find a positive t such that b can be written as e power t. That means that this function, so what I said, this is true for any a, this is true in particular for e. And that inverse function is usually called the natural logarithm. Actually, one can talk about logarithms on different bases. So they log to the base e, and some places, typically the Americans, write this symbol for the natural logarithm, for the logarithm to the base e. So anyway, so all this is all had. I know you know all of this, but I think it is important to see that all these things are completely natural and they're forced on you. There's only one way these things can be defined, and they have to be defined. If you want to make sense of the most natural constructs. Okay, and then one proves that this has some magical properties. Okay, so what do I want to say? So, for example, it is true that so this function is a perfectly nice is a differentiable function, and its derivative is itself, as you just saw. Because the derivative at 0 is 1, it will follow the derivative anywhere is itself. So there is a unique function which is its own derivative. And then if you believe, that means it is infinitely differentiable. Once you have a nice differentiable function, the natural thing to do is to write its Taylor series, or Maclaurin series, to try and get polynomial approximations, if you can, of this function. So you would expect this to have some a series expansion, right? I've got it Cn. Now you know that these Taylor coefficients are unique. The unique way in which you can write it as a series. So this series will be convergent at least for values close to any x at which this function is differentiable, infinitely differentiable. So, but then you know that you can differentiate if you look at the derivative function, it will be obtained by differentiating the series. And so what you can see is that n times Cn will be Cn plus 1. You just differentiate. You just differentiate the series term by term. You know how to differentiate x power n. And then the result, differentiated series must be the same as the original series, from which you can see that the coefficients must satisfy this relation, from which it follows that they have to be the familiar reciprocal or the factorial. Okay. In fact, I will make one tall claim here, which is that if all mankind were to be wiped out and you had a choice to leave 2 lines of symbols that alone could be viewed by in the future by mankind, then I think these 2 lines will give them all of mathematics. The exponential function contains in it everything. So let me illustrate why I am making all these tall claims about the exponential. For example, this series, to make sense of the series, so actually maybe if you give me a third lane, then I will say where x is what? I will make that as a third statement.
NCN is Cn minus 1.
Huh?
Cn minus 1.
Cn minus 1.
It's 1 over n factorial.
Yeah. Okay. So in Cn minus 1. Yeah, if you differentiate this series, you will come down. Yeah, sorry. So there is a series where the coefficients are given by this, and I'm finally asking for what x. This series makes sense for what do you need x to satisfy in order for all this to make sense? Right? So I just want to say that I should have some system, some number system, where I can multiply 2 numbers. I will be able to take powers of a number. I will be able to add numbers. And I must take infinite series of numbers. That means the notion of convergence should make sense. So for example, this will make sense for x in n by n matrix. You take an n by n matrix, then every term of the series makes sense. You know how to multiply a matrix by itself any number of times. So you can form x power n by n factorial, and I can write down this infinite series. What does that mean? At the nth stage, what do you mean by series? You take the nth stage, sum up to n, you take the partial terms, sum, what do you call it? The partial sums of the series. Those should converge. So we take the partial sums of this series where x is a matrix, then the nth partial sum will be a matrix. And it makes sense to say that a sequence of matrices converge. What does that mean? For every ij, the entry ijth entry there must convert to the ij entry there. So it is true, and one can prove once one sees the magic of this exponential function, that this series does converge. So it makes sense to talk about exponentials of matrices. It makes sense to talk about this in any system where you can add, multiply, and take limits of convergent series. For those of you for whom these words make sense, this makes sense in any Banach algebra. It must be a Banach space. That means you must be able to make sense of convergence of series. It must be an algebra. That means you must be able to add and multiply things. Okay. Now, in fact, this must make sense. It makes sense even in Banach algebras which need not satisfy the So let's go back to playing with exponential functions. So we know that usually e power x plus y will be e power x, e power y. Yeah? But unfortunately, when you go to the kind of generality that I'm talking about, if you let x and y be matrices, then x plus y is commutative. See, this side doesn't care about the order in which x and y are chosen. But matrix multiplication is not commutative. It may be that e to the x and e to the y do not commute. So the answer may be different, but this forces them to be the same. So this, in fact, is not true. Is not true as stated. But there are very useful versions of this which are true. One, it is true if x and y commute. That means xy equal to ix. If x and y commute, then one, and the proof is exactly the same as the proof for numbers. You prove that e power x plus y, where x and y are numbers, is e power x times e power y. The proof that you give for that, the same proof can be adapted to prove that this holds whenever x and y are matrices which commute. Okay. If they don't commute, what can you do in general? There is a beautiful formula by, it's called the Trotter or Trotter-Kato formula, which says that e power x plus y will be, I believe I've got this right, e power x by n, e power y by n, power n, limit, and then goes to infinity. That means you take e power x by n, y by n, and then if you take that power n means you take that into that. So if they don't compute, then you'll have, for example, for n equals 3, this looks like e power x by 3, e power y by 3, and then the same thing 3 times. Things don't commute, so you can't write them in any order you want. So somehow the lack of commutativity is made up for by going to this limiting process. So this is an extremely useful fact, which is used in much greater generality than just for matrices. It is used for even at the level of so-called unbounded operators in Hilbert space. Okay, so let me just talk about further wonderful thing that the exponential function can do with. So I said you can make sense of the series whenever you're working in a number system. In particular, you can work in the number system with complex numbers, where you can add two complex numbers, multiply them, and convergence of a series of complex numbers makes sense. And the same formula, the same series will define a complex number. So z going to e power z will give you a map from complex numbers to, in fact, you can never get 0 in the image. You will get every non-zero complex number as the image of the exponential function. Now this fact itself, that every non-zero complex number is the image of some number under the exponential function, this itself is the starting point for one whole area of mathematics. A whole notion of fundamental group, various things, they come from this. And for example, so let me just say one other thing. You know that, in fact, if you specialize to z equals, so any number you can write as mod z times e power I theta. Right? So there is the usual real complex number z. There is mod z. And if that makes angle theta with the x-axis, then you can write it in this fashion, where this is the exponential function defined in this fashion. And because what I am saying is that, so if mod z is equal to 1, then I am saying I have just e to the a theta, z equals e to the a theta if you are on the unit circle. But that means if I add 2 pi to the theta, I don't change the point. And if you take now 45 degrees and take 360 degrees more, then you are at the same place. So we see that this function is periodic with period 2 pi I. That is, if you write the z as, so this is something that you would have seen. So if you write z as x plus iy, then e power x, if there is the usual decomposition into the real and imaginary parts, then e power x will be the modulus of z, and this y will be the argument of z. That means e to the iy will give that angle part of z. And in fact, e power iy is, you would have seen this amazingly beautiful theorem. All of trigonometry is contained in the exponential function. And you can recapture all of that from just the exponential function. And in fact, okay, let me conclude with just one more wonderful feature of the exponential, and then I'll go to something that Paramit said one should talk about. So I have some numbers for this. So. Okay, so another example. See, you know that in the real line, Okay, in the complex case, I said the range of the exponential function is everything non-zero. In the case of the real line, the range of the exponential function is what numbers look like e to the x for some x, for x real, what are the possible values of e power x? It is just exactly all positive numbers. Okay? You can ask the same thing if I take e power x for x matrix, n by n matrix. What kind of matrices will I get? Will I get all matrices? For okay, so I want you to observe the following. I want to give you one argument to say that this is not all positive matrices. I want to say that you can only get matrices whose determinant is positive. Somehow there is some positivity inherent in the answer, which also is something with great topological implications. So, see, for example, if I look at f of t equals e power t times x. So t is a number, so t in 0, 1. So I have, so this is a path of matrices. Here the collection of all matrices. Inside here I have this curve f. What is f of 0? F of 0 is the identity matrix. And f of 1 is the matrix e power x. Okay? And we know that the exponential function is continuous. So this, you can think of this as a composite of two continuous functions, t going to t power x, and then you take the exponential function. We know that the exponential function is continuous on all matrices. So if you take the composite, that will be continuous. So there is a continuous path of matrices. Okay, and this is a continuous path of matrices, then determinant of f of t is also continuous, because determinant is a continuous function of its argument. If you just perturb the matrix by a small amount, then the determinant is not going to get changed by much, because determinant after all is just a polynomial in the entries of the matrix. Okay, so determinant of f t is continuous, and when t equals 0, the determinant is positive, and the determinant can never be 0, because if so I'm saying that e power x is always invertible, because x and minus x commute. E power x times e power minus x is going to be e power 0, which is identity. So e power x is always invertible. That means this is a curve of non-zero numbers, curve of non-zero real numbers, which can never be 0, and it starts at 1. So it must always be positive. Is that clear? Conclusion is that therefore determinant of e power x is positive. Then if this continues a function of t equal to 0 is 1, it has to be positive for all t. At t equals 1, it gives me determinant of e power x. So for all, even among matrices, the innumerable ways in which the exponential function plays a role in, see, this thing of taking exponentials of matrices and looking at these paths of the so-called, see, if you look at f of t equals defined by t going to e power tx. This is a homomorphism. See, R is a group with respect to multiplication, with respect to addition. So T1 plus T2 will go to e power T1 plus T2x. But because T1x and T2x commute, you can write that as e power T1x times e power T2x. So among the matrices, one has the so-called invertible matrices. This actually lands in here. And this is actually a homomorphism. It is a continuous homomorphism from the real line into the group of invertible matrices. Now this is the starting point of much of analysis. What is at the basis of things in study of Lie groups, Lie algebras, various, and they're just the tip of the iceberg. The exponential function is what underlies almost all analysis that one can think of. So finally, let me just stop with something completely disconnected. I want to talk about something that Paramesh has told me that I should highlight. In the certain kinds of logical thinking does not come naturally to our students after they do take the standard state and prove so and so theorem kind of exams that all our BSc students face. They are not able to apply their mind to just analyze rationally some situation. For example, at one stage when we were interviewing students, I was advocating the use of the following question to single out students who should be considered seriously and certainly single out students who should not be considered seriously. Namely, my question was, okay, as soon as a student comes, I'll say, you know what it means for a sequence of numbers to be a Cauchy sequence. Okay? And people will come up and say, yes, for all epsilon there is a delta, so that blah, blah, blah. So what does it mean to say that Xn is not a Cauchy sequence? I want an epsilon delta answer. You will be amazed at the number of people who cannot come up with the correct answer. What is a Cauchy sequence? So, is a Cauchy sequence is for all epsilon, there exists delta, and then for all n, not delta, so there exists an n such that for all n greater than or equal to n, if you are in a metric space, then you say distance from Xn to Xm, less than epsilon. On the real line, you will put modulus, so the difference. So this is what it means to say that Xn is a Cauchy sequence. What does it mean to say it is not a Cauchy sequence? So, I think it is good to teach students the following simple mind. If you just ask people to answer the question, what is not a Cauchy sequence? If they haven't thought of it this way, then you will find various possible orders in which the quantifier there exists, and for or and not will come into the answer. But actually the answer is very simple. It is just you want so I want to say that the negation of a statement is the same as you just change all the quantifiers to the opposites. There exists epsilon positive for all n greater than 0. There exists n greater than equal to n, such that the negation of this holds. That means distance from Xn Xm greater than equal to epsilon. So I am giving you a mantra of how one translates one statement with qualifiers, universal and existential quantifiers, into a statement. And then the reason is that this is really the whose laws is it? De Morgan, right? There is the De Morgan's laws, because they say that look at P as a property that P of Nm is a property that D of Xn Xm is an epsilon. It is a property of a pair of integers that the distance between those two things is less than epsilon. Now this statement can be thought of as saying intersection over all epsilon positive union over all n intersection. Sorry, m and n I should have had for all m and n. Of the set of all mn with that Pmn holds. This set is really just this intersection union statement of a certain domain. Those things in the domain of some function which satisfy some property. And so the complement of such a set, you know by De Morgan's law that the complement of an intersection is the union of the complements. So by De Morgan's laws, you see that the negation of this has to be the negation of this, has to be given by this. So this is something that I think it is good to teach students within the first month of their, even first week of their analysis courses, so that they get their reasoning straight on. You want to say something is an abelian group, when is it not abelian? You want to say something is some kind of Hausdorff topological space. When is it not Hausdorff? Hausdorff means for every pair of points x and y, there exists an epsilon such that epsilon bar about x and the epsilon bar about y do not meet. So, when is it not Hausdorff? Earlier you had for all xy you can do this, now you say there exists an x and y which cannot be separated. For all xy there exists epsilon. There exists xy for all epsilon. For all epsilon the epsilon bars will intersect. That is the negation of Hausdorff space. Okay, so I think I have taken enough time, so thank you very much.
Video consent for the video.
உடனே கை தருகிறல்ல
Yeah.